Okay, so the title already announced is the historical vulnerabilities in the automotive space. My name is Andreas Weichslgartner. I work at CARIAD as a security engineer. As said, I developed a study infotainment system, so I eat my own dog food. And besides that, I'm also working on integrating security tests in our CI/CD pipeline, working on fuzzing machine learning. My information communication technology in 2010 from the University of Erlangen, then stayed at academia until 2017 and got my PhD in computer science. Then I switched to Audi Electronics Ventures in 2017. And since then, I'm working in the automotive industry area of security. So short disclaimer in the beginning. So I will present some vulnerabilities. They are all publicly known, so there's nothing secret in here. They're all fixed. And yeah, so this is about educational purpose, not to blame anyone, but just to learning from the past. And also it will be focused on the car side itself, and it will exclude like the key fob range extender stuff, because this is more a technological vulnerability and not so much a software vulnerability. With that said, so our goal is to learn from the past, that we don't repeat it today. So this is the goal. Or as Captain Hindsight would say, like, it's always easier to give advice after it happened. So so probably you should have written this 64 bytes into this 32 bytes buffer. Yeah, so just going straight to the list of the most dangerous software vulnerabilities, which is always released by Micro every year. And it changed a bit over the years, but still we see that the most dangerous software weakness is the out of bounds write. So this is still number one, has a very high score. And then still also follows some out of bounds reads. This is also, like we see on the right side, these are the memory safety problems, which only exist in languages like C and C++. But we also have some other weaknesses like command injection, and yeah. So, and these are some of the weaknesses. I will give some examples in known vulnerabilities from the past where these weaknesses appeared in the automotive space. And as this is an automotive security talk, we of course have to start with the GPAC, the most famous automotive hack ever. So it was in 2014. Charlie Miller, Chris Velasek, I think you all know the story. So they attacked a Jeep Cherokee over Wi-Fi, and they could just basically gain control over the whole car. They could inject CAN messages, they could brake, they could activate the wipers, and yeah, and basically drive the car off the road. And as a result, Ford had to recall 1.4 million cars. Jeep Chrysler, they had to recall 1.4 million cars, and their stock went down. So it had some real impact on the company. And yeah, so what was the problem? The basic vulnerability itself was very boring. So even in the report, Miller and Velasek wrote like they wished it would be more spectacular. It was just 4 lines of Python, which they wrote. They connect to some inter-process communication bus, and then they could just write, yeah, please execute this command, and like netcat was installed. So in the end, it was just connect to service and start the shell. So this is very easy. And so, of course, they did more stuff. Then in the end, they connected over mobile wireless, like not only Wi-Fi, but also the mobile network. And they reflashed the firmware so they could inject arbitrary CAN messages and so on. But the initial access was done via Wi-Fi and like with these 4 lines of Python code. So what is the problem here? So the problem was that basically the debug ports or ports were open which shouldn't be open. Besides that, like there was no input validation of the execute command, and it was a operating system command injection, so they could just pass any command into this inter-process communication tool, and then they could execute what they want. And so also there was no access control who can access this dbus interface. So if you know the port, and you could connect, and then you can execute code. So these were the weaknesses which were present in this vulnerability, and how you could detect this. So like, imagine this was implemented with a system in C. So this is a function call which just executes everything which you give to this function, and it will start a shell and then just use the string which was passed and execute everything in it. You could use like clang tidy, for example, and check for certain coding guidelines, and it will tell you, hey, you're using the system function, you should not use this system function because like it violates the coding standard CERT-C rule N33 something. And yeah, it also this works for like popen with this static analysis. You could also do some taint analysis, like for example, also in the Clang static analyzer has some taint analysis, which tells you like what are your information sources, for example, like reading from standard in or reading from a network, and then you pass this data through several calls into a sync-like system, and like the system sync, the connection between the sync and the source in such kind of functions, they shouldn't be like direct. So you shouldn't be possible for an attacker to control the input of a function like system. And like this static analysis tool would give you then this nice visualization and show you like where from the input you leaked your command into your system function, and where the input was tainted and where the tainted input was then executed. Of course, you could also use like tools like CodeQL, which you can use like in GitHub Advanced Security. It also does some taint analysis for you. This is also some predefined checks in there. You could also do this manually, but out of the box, it will also warn you about when you use command injection for this, and it will also tell you you have a tainted input and you use it in a certain function which shouldn't execute tainted input. So this will give you also this result and tell you, okay, this is a critical issue, and it is this kind of CWE weakness which it violates. You could also, of course, use fuzzing. We are at FuzzCon, so how we could use a fuzzer to detect OS command injection. So imagine it was like built with Java. So sometimes in the infotainment systems, we use Java. So with Jazza, you could use like a custom hook, which uses the function where you execute your program, and it checks that the first parameter, for example, in this example is like process builder, and process builder should not be controllable, the first argument, by an attacker. And it will check if the first argument is this predefined keyword like jazz. And if it is, then we abort and give this result that we found, that we found this vulnerability by fuzzing. We could also use this technique for C-based or C++-based fuzzing. So we can say we can mock or like link the libc library, write our own system function, and like which intercepts each call to system. And if this system call is made with a certain string in the beginning, then we can throw an assertion and terminate the program. Otherwise, we can call the real system function and pass forward the arguments. And we can also then build our fuzzer, start the fuzz, and we also will get a result that we have a deadly signal because our assertion failed. And if we then dig into the finding, it will give us the stack trace and tell us where our assertion failed. And yeah, with this kind of thing, you could basically fuzz all C functions in libc. Of course, there you have to do some manual effort, like for Chaser, there are already some predefined sanitizers for this kind of injections, because in Java, you don't have all the memory issues, so they have other bug finding sanitizers to find this kind of bugs, while in C and C++, the main focus is on memory weaknesses and undefined behavior. So they're out of the box. You use normally the memory stuff, but you could also write your own intercept and then assert on certain strings. So let's go on to a more more current attack. It was like from 2020 when Ralph Philipp Weinmann and Benedikt Schmotzle from ComSecurities, like they attacked the Tesla Model 3, and they could open the doors and like without any click could control the car. So how did they attack the Model 3? They used Wi-Fi. And to make the attack more shiny, they used a drone. So they mounted some evaluation board on the drone, and then could like trigger this zero-click vulnerability from the drone. Their entry ECU was the infotainment, and the vulnerability was inside a connection manager called Conman. So this is a formerly developed by Intel, then open sourced, and I think was then a Debian package. And yeah, so they could control door lights, unlock the car with a zero-click. So this was very nice. And how did they find this vulnerability? So they used the fuzzing also. They used the AFL fuzzer. They took a look at the source code. They saw that it was all like pure C, mem copy all around, and the code like looks like crappy code. So they fuzzed it, and like within no time, they found a crash in the DNS proxy. Then they did further research, and they were able to exploit with two vulnerabilities. So like one was this stack overflow where they had a partial write inside the system, and the other one was an out of bounds read where they could then leak some addresses to circumvent the ASLR mitigation. So in the end, they had like these two kind of memory weaknesses found, and in addition also they used some kernel bugs in the Linux kernel to get the full access and full remote code execution inside the car. And if you see like the fixes here, like basically you have to add some more checks that in your mem copy you don't have an out of bounds write, or in the other case you have more checks that you don't have an out of bounds read. So this is common problems with C, that often you forget some checks, and with fuzzing it's easier, or you can detect such cases where you forgot your checking. Then 2 years later, like David Berat and Moussa Dehor from Synactive again tried to hack a Tesla Model 3. Again, they used Wi-Fi infotainment, and they used the same network manager. So the vulnerabilities in the network manager, they even named the vulnerability like T-Bone 2.0. So the original hack was like T-Bone, and now we have T-Bone 2.0. And again, they could control the car without any interaction from the user. So it was also zero-click attack. And yeah, so this time, again, we have two CVEs they found. It was like one was an heap buffer overflow where they could swap one byte, like from OA to 0, and the other one was a double free. So this two components, a bit different subcomponents of the con manager. So this time it was not the DNS, but like the Whisper is a hotspot detection module, and GWeb is like it's an implementation of HTTP GET POST queries. So with these two bugs, they could also gain a remote code execution. In addition, also they found like some Linux kernel bugs to get the full exploit chain, and like they spent 1 year of research on this. So this is not trivial to exploit, but in the end, again, we have two memory safety issues in the same module again. So let's take a look at the CVEs issued for the conman. So we saw until 2020, so before the first Tesla hack of this kind, like there was not much big security vulnerabilities found in this module, and one could think, yeah, like very secure module. We couldn't find any CVEs there, we can use this. But then if someone started to dig into this module, then they found, like in 2021, they found some bugs in there, and then later again in the same module, they found bugs again. So it's like, you know, just before people didn't look at this module, and when you start to look, you will find bugs. So this is also gives you sometimes a false sense of security if there are no CVEs for a certain module. So maybe it has a lot of CVEs, but no one took a look at it. So one approach here is like from the Open Software Secure Foundation. They have something like called like scorecards. That's how they want to quantify the security of an open source project. So they have like 5 different categories, like code vulnerabilities. So is there any known vulnerability for this code? How is the maintenance? How is the testing, and so on? And then they build a score from 0 to 10, and then you could, from this score, you can determine how secure the development of this software component is. Unfortunately for Conman, you can't evaluate the score because this is not hosted on GitHub, and the scorecard only works for GitHub. But if you take a look at some of the criteria, for example, the continuous testing, so they write, do they have CI tests? Do they use fuzzing? Do they use like a static analysis tool? And if you take a look at the Git repository of Conman, like this is these are the unit tests. So they have like 2 unit tests. Of course, they have some integration tests, but like the unit tests, they only have 2. And they were written by BMW, so probably Conman was not only used by Tesla, but also by other automotive vendors. And in the end, like we have like 2 unit test files, and we don't have any other more testing stuff in this, at least which you can find in this repository. There's no CI, there is no fuzzing, there is no sanitizers, and so on. And given that like a communication manager, so it has a huge attack surface, so it connects to wireless, and like everyone can connect to it. And given this attack surface, there should be a lot more testing, and also the whole industry should invest into these kinds of modules which have such a role inside your infotainment system, for example, because they provide the first entrance to your system. Yeah, so this was basically the 2 Tesla hacks based on this same software module Conman, and hopefully, we move on to some other communication managers. And the next hack is a CanFD hack. So this was presented this year at Black Hat Asia by Ariel Kadishevich and Shaki De La Rea from Argus. And so here they attacked, like before we had infotainment systems, now they attacked an instrument cluster. The difference is here that this is not like the other infotainment systems were running Linux. And here we have a system with a Renesas processor. So this is more embedded and has a different processor. It doesn't run a full-blown operating system. And yeah, so they were able to attack this directly over CAN. So they forged the CAN messages and to trigger a stack overflow in a CANFD receive. And then they could trigger the backlight of the instrument cluster. So here the vulnerability itself was straightforward. Here the challenge was more to craft like CAN messages to get a reverse shell over CAN. So this is yeah, the interesting part of this talk, how to get access to this ECU over a CAN and not, for example, the Wi-Fi in the other hacks. So how could you detect this problem? So as it's they said like there was a buffer with 32 bytes, and like CANFD messages can have up to 64 bytes of data. So it's a classic stack buffer overflow. You can detect this with fuzzing. So if they would have write a fuzzer, like I don't even know why they used like a 32 byte buffer, because like normally CANFD messages 64 bytes. This is a static size for the max size. It's defined in normally in your CAN stack. So I don't know, I can only guess why they didn't do it with a 32 byte. However, like if you would use fuzzing, you can detect such bugs pretty easily. And then to fix this kind of bugs is also much easier than to write an exploit for this kind of weaknesses. Also, there is a link, you can try this out online and yeah, see how the fuzzer will crash. And yeah, what you can also normally do is like if you can't switch to Rust. So of course the classic mitigation for all memory safety problems is like don't write it in a memory unsafe language. So switch everything to Rust. However, this is of course not feasible in every case, and yeah, it will take time to switch to Rust for some parts. But there's still some mitigations you can use, like in C. So you can still compile, given your compiler supports this with some mitigations. So fortify source. You can use this in libc, and also Clang supports this. And I think also like in muscle libc, there are some ways to use fortify source. So this will give you some bounce checking and makes it much harder to exploit and buffer overflow. Also, if you look back to the first stack smash for fun and profit, I think was from 1996. If you would execute this on a modern machine with all mitigations enabled, like it wouldn't work like this. So there has been a lot be done in this space. So if their mitigations are on, then it's much harder for an attacker to exploit this kind of weaknesses. We also saw this in the OpenSSL and the recent OpenSSL bug, which was downgraded later because like it was very hard to exploit. Yeah, so this was the state of the art which we are living in. And so what are the, how we can tackle this? So memory safety is still a huge issue, not only in the embedded device, so also like Microsoft, Google, Chrome, they all have still a lot of portion of memory safety bugs. And OSS Fuzz also still finds a lot of bugs which are memory safety. And yeah, so some trends, they are maybe shifting from like overflows to use after free bugs, for example, in the Chrome project. But still, its problem is the memory safety, in the whole. And it seems like it won't go away overnight. Still, we have fuzzing and everything, but still the problems are there. However, also there are some new mitigation proposals. For example, for the standard libc++ library in Clang LLVM, they proposed that we use like hardening the buffer access in C++. So every time we access a vector or a span or something, and we access it out of bounds, that we don't have undefined behavior, but that the program crashes. So from a security standpoint, of course, this is much more desirable that your program crashes instead of like being an undefined behavior and being exploitable by a attacker. So if you maybe in some cases it can have some like performance impacts, but in the automotive space, like security is a much more concern than the performance. So in our case, like, it would be nice to have this kind of hardening techniques that our like out of bounds access will then crash there. Another mitigation was proposed in the Chrome project. So they to tackle the use of the free bugs, they introduced a new kind of pointer, and it's called miracle pointer, and it does some ref counting, and after you, for example, free some memory, it will poison also this kind of memory area, and when you try to access, you will also get a crash or a bug, and you can detect this kind of use of the freeze, and it makes it harder for the attacker to use this use of the free weaknesses. And there's one other proposal to zero initialize objects on the stack. So basically, if you don't initialize your variables, this can also be exploited. And to use like zero initialization for all stack variables, the author claimed that it could have like eliminated 10% of all CVEs. And so Ruben Planet is also a Toyota company, so he's also working in the automotive space now, and will in our case, like, there are also concerns about performance, but they also said like it has zero performance costs. Only in some cases where you have huge stack variables, there you can like opt out from this feature. So let's see how if this feature will go into the future C++ standards. Another thing is like C++ core guidelines. Like, as an example, there are other guidelines, but these guidelines should prevent you to use like unsafe elements of the languages, and like use like, for example, the TSL. They offer some bounds checked access to vector, like to spans and so on, and like don't use naked new deletes, don't use malloc and so on, and with this kind of guidelines, it tries to prevent you from the bad corners of your language. Also, then there was a proposal from Herb Sutter. He's also working for Microsoft. He's in the C++ standard committee, like some new syntax CPP front, which you then compile from CPP front to C++, and like CPP front then basically uses this core guidelines and makes it impossible to use this kind of unsafe languages. It's very experimental, but let's see what comes out of this corner. There's something from Google, like Carbon. Also, there's some successor language to C++. Similar, you can then interopt with your C++ code, but have a better language to write new code. It's like Kotlin to Java, TypeScript to JavaScript, and so on. And also very alpha stage at the moment, but and see what we have in the future there. And so let me finish with some code. So John Carmack from id Software, famously known programmer, they wrote everything in C back then, and he said like when he discovered some tooling to check for bugs, he tried out all the tools, and like even his code, he found a lot of errors using tools. So that just should show you that however what a good programmer you are, you still will produce a lot of errors in C and C++, and it would be like you should use all the tools you get your hands on and use these tools to make your code more secure. That leaves me with my summary. So I showed you some vulnerabilities in the automotive space from the past. Use this to learn from your future if you implement something similar, or use some third-party software which you want to use in your infotainment system or in another ECU. Like, take a look at it. How is the software written? What could do there? Like, could add some fuzz cases. improve the software quality of this third-party software, use something else. And if you know that you have some constructs with getting unsafe data or uses some pointer arithmetic on something like this, so this is very hard to do correctly. So there you should test enormously if you're using such kind of constructs. Yeah. So contact me with my first name, second name at CARIAD Technology, and let me conclude with Fuzz over things now. Thank you.